Thank you, everyone. Thank you for giving me the time to introduce what we have done recently. And I'm going to talk about the high performance computing for secure non-volatile memory and edge AI applications. And just a few, for people who do not know me, I'm leading the computer architecture and storage system laboratory. And the main purpose is to speed up the data access and resource sharing. And the memory is still become a bigger issue in the big data era, right? Even we are in the AI, big computing era. And if you look at the training side, and it involves a huge amount of data movement. And if you look at the technology trend in terms of industry, how to make the memory, and look at the right diagram showing, there is a projection and the number of the petabytes shipment by 4 major memory technologies are still growing and always in last 10 years and always keep going in next 10 years. And the total memory market is a 440, actually it's 44 billions. And NAND flash, DRAM, 3D X-point, and magnetic RAM, those are still the keep pushing the memory size and memory capacity in double every 2 years in this rate. And specific technology make this happen is from you can see from the left diagram, Samsung and have all other different companies roadmap to make these increasing the total number of layers and increasing the number of density to make this happens. And these are some tables showing the how NAND 3D flash layer they're keeping using the innovative packaging techniques to increase the memory capacities and memory size. And but there is a fundamental technical challenge for us to make use of this keep growing memory stuff. And one thing is like NAND memory technology have the recognized the limited endurance, and each cell has a limited number of the write erase cycles. And if you keep writing to the same cell for too frequently, it's going to become malfunctions. Another challenge is the slow write issues. And in NAND flash memory, you have, before you do the write the new data, you have to erase the whole memory, whole page package, and before you write the new data. And the good thing can be bad thing, like since the NAND flash and persistent memory is called non-volatile, the data still stay in the event of power failures, but that we can also leave the room for the security attackers to attack the data, right? And the information can be easily leakage. And solution will be the encryption and trying to reduce the amount of data traffics. And we identify several application, performance bottleneck, and taking place in the basic memory and storage, operations, and one or multiple copies that's going to cause severe problem on using these big NAND memory as the main memory systems. And copy and write is one of the common case, and it has a different using widely intensively use this in computer memory systems, and we need to figure out a way to resolve it. And in today's data center, there's also even more copies taking place in different sensors, different cloud, and different servers, and in terms of different backup supporting stuff. And there's a room for us to resolve these performance issues and how to make the data movement more efficient, more effective, and using some zero copy techniques we're investigating. And this is one of the recent work we, trying to leverage in the existing security counter, trying to address the performance bottleneck taking place using these existing split counter to attack the multi-memory copy issues for copy on write in particulars. And another topic I switch is to the edge computing. So, these edge computing is the current research wave, and we are not going to move every data to the cloud. We are going to do a lot of AI, edge AI. We're doing the edge learning on the edge devices, and which is closely to the sensors itself, and to save the data transfer, stuffs. And the challenge is, you are not going to use the same model, and you are not going to have the same computing power, same resources, right? And running and launch the computing applications on the edge platform is resource constraints, little scalability, and not support of the trainings. And the edge clients often may not be able to facilitate the full precision of the AI model, right? And not like the Microsoft Azure cloud running these 256 billion parameters of models. And given the limited computing cycles, limited network bandwidth, and limited energy budget, then how are you able to redesign your model or redesign your computer hardware in order to meet the edge users requirements? And one particular example is how do you launch the inference, like at different edge clients on heterogeneous hardware devices, right? And today's edge devices can be vary from the TPU or GPU, or NVIDIA's GPU and Google's TPU and Intel's VPU, and even the CPU, those different kinds of hardware devices. And we are conducting the several research tasks. One of the thrust we are looking at is given a pre-trained AI model, how to identify a good edge hardware to support it and to make a more to meet the power budget and the latency budget, right? And given the different kinds of vendors, right? Intel, VPU, Google's Edge TPU, right? NVIDIA's GPU, and commodity CPU, and how to identify appropriate hardware that can facilitate this specific pre-trained AI model. And this we develop a cross-model based framework at this moment. And if you look at the specific features of the models, and if you consider the static and dynamic sparsities and structure and unstructured sparsities and loop order from the compiler stuff, and how we are able to identify, find the good appropriate hardware to fit it. And one particular example looking at is a graphic convolutional neural network application, which is widely used in the recommendation system, and this linked many large graph and with many connections. And the problem is we have the input at the graph, right, and then going through the aggregation and combination stage. And we have the input parameter from the input data sets to try to capture the model's features, and as the input, then we are running different kinds of operation algorithms and trying to meet the different requirements from the hardware in terms of the latency, energy, stuff. Then we're able to output the appropriate hardware stuff. And second, the research thrust we're doing is let's say we go the other way. And the last research thrust we're looking at is That's we have a fixed pre-trained model and how we are able to come up with the best hardware solution. And if you look at back and given the certain constraints from the hardware, right? Given the limited hardware, for example, in the last speaker's edge space computing, if you have a very limited FPGA and that's the resource you have, then you already have the latency requirement and the power constraints, and then how do you design the appropriate AI models, right? DNN model, deep neural network model, for example, right? And there's million number of the AI models out there. AlexNet, VGG, ResNet, there's so many huge, large number. And some, believe it or not, we know these models some models are giant, some models are, so might have many layers, and it's not easy to fit on this specific hardware, right? And the thing is like our solution, we're trying to develop a fast, efficient, effective, integrated model systems hardware framework, and with considering the network and the bandwidth, parallel model detections, and all these are the design objective would consider single edge versus the edge servers, and how we're able to develop this integrated framework to identify the best the models. And one particular use case is if we have the new data keep going generated, right? We must upload it from the end devices, not the cloud, to retrain data, and then we may be able to given the little access to the data and give the limited constraints of the resources, then how we are able to design an appropriate model and which can fit into this the overall into the whole environments. Okay, this is the we thanks the support from the National Science Foundation, Army Army clusters, and some researchers from my lab. Now I'm able to answer the questions.